So there's a certain irony that the chairs have just arrived for the panel that kind of illustrates some of the inherent challenges in a microservice architecture where messages arrive late. So welcome to my talk on maintaining data consistency in a microservice architecture, which sort of follows on quite nicely from Randy's talk where he provided a good overview of the challenges that you'll face dealing with data in a microservice architecture. And it really turns out that dealing with code, splitting that up, that's the easy part. Dealing with the data, which now gets distributed amongst a set of databases, that ends up being the real challenge. And so as Randy illustrated, there's problems with querying, and there's patterns for that, API composition and CQRS. And then there's also problems with maintaining data consistency. And so that's what I'm going to talk about. And then as Randy mentioned, I'm going to describe a pattern for maintaining consistency in a microservice architecture known as a saga. And it turns out it's kind of challenging. This is one of the downsides of using the microservice architecture is ensuring data consistency. But in a lot of cases, it's a good idea. But before I talk about that, a little bit about me, if you don't know me, then I got my start in programming 30-odd years ago, building Lisp systems. So runtimes, compilers, tools, and et cetera. Eventually programmed in Java, wrote the book Pojos in Action, which was all about Spring and Hibernate, which 13-odd years ago were revolutionizing enterprise Java development. And then then back in 2007, started tinkering around with this really obscure service known as EC2 from an online bookstore. We know how that turned out. Look, I got so excited by the concept of being able to provision servers with APIs that I created the original Cloud Foundry. So that was a Java PaaS for deploying Tomcat war files on EC2, spin up a bunch of EC2 instances. And then that was acquired by SpringSource back in 2009, right before it was acquired by VMware. So I ended up spending a bunch of 4.5 years at SpringSource, VMware, and then part of Pivotal when we were sort of somewhat ejected out to create Pivotal. But that was a while ago now. And so for the past 4 years, I've been pretty much focused on the microservice architecture, which actually grew out of my experiences building the first Cloud Foundry that was a monolith, and we had issues with that, even though we were only a 2-person team. And then, that prompted my interest in microservices, and there was a lot of synergy between that and the new Cloud Foundry that I was sort of involved with evangelizing. So I just kind of carried on, and so I've just spent the past 4.5 years doing consulting and training around the microservice architecture. Also have a startup creating a platform that's built, or that we're creating a platform for developing event-driven business applications. And the motivation really is to solve distributed data management challenges. And then I also had forgotten how traumatic it was writing a book, so I'm doing it again. And it really is traumatic. But I'm getting close to being done, hopefully. And you can get an early access version of that from Manning. And then if you want to know more, go to learnmicroservices.io. So that will point you to a whole bunch of resources, including Microservices.io, that's a collection of patterns that I think many of you have visited. Okay, so the agenda is going to talk about why ACID is not an option, at least between services. Within a service, you can certainly use ACID transactions, just not between them easily. Talk about the Saga Pattern, and introduce the idea, talk about some of the challenges, and then I'm going to describe some implementation issues, like how do you make Sagas go, and then how do the services that participate in a Saga communicate. So that's the idea. So I'm going to begin with the obligatory summary of what the microservice architecture is. So it's an architectural style that structures an application as a set of loosely coupled services. So instead of building a big monolith that's sort of difficult to deploy, or develop and deploy, you build a set of small applications or services that are loosely coupled. And the whole point of doing this really is to enable the continuous delivery, or specifically the continuous development of large, complex applications. And the microservice architecture supports that in two ways. First, it gives you the testability and the deployability you need in order to do continuous delivery and deployment. You know, the services are individually easier to test. They can be deployed independently, so that's good. And also, this architecture supports the notion of having small autonomous teams. You know, you have a small team, they own one or more services, and they have all of the skills in order to go from requirements into production. And with this architecture, they can do that without coordinating with any other teams, except when teams have to agree on APIs because their services need to communicate. So that to me is the essence of the microservice architecture. So when you apply that to, say, sort of, I got this fake application, an online store, you end up with a system that looks like this. You got a bunch of services. Each service has its own database. As you're going to see, that's essential for loose coupling. They're fronted by an API gateway, say, that provides a uniform interface, basically a facade into the set of services, and they're consumed by various clients. So what I'm really going to focus on is this whole notion of having private data. And I just want to stress that, you know, having a private, what I'm calling a database, doesn't mean a private database server. You're not now giving 10x as much money to Larry Ellison for extra Oracle licenses. They can still be sharing the same database server. They're just going to have their own database schema. So it's isolated, private, you know, encapsulated data. That's the key point. And that's really important to ensure loose coupling, because if services access one another's data or one another's tables, that would get in the way of development. If I'm working on the order service and I wanted to change the order schema, and it was being accessed by the customer service and 15 other teams, that means I'd have to arrange 15 other meetings to schedule that schema change. That gets in the way of continuous delivery and deployment. So by each service having its own private encapsulated data that's only accessible indirectly through that service's API, we ensure that we're free to change effectively the implementation details of our service without any coordination. So that's the motivation. So in this example, customer service has the customer service has the customer database, the order service has the order database, and they communicate via APIs. Could be REST, but as you're going to see, that it's in fact going to be messaging. But that then creates problems. How do we maintain data consistency? You know, this is the problem. How do we implement transactions that now span services? And this is really important in order to enforce invariance. So in the case of this example with orders and customers, customers have a credit limit. And we must enforce this credit limit at all times. Otherwise, we've sort of violated some important business rule. In a monolithic system, that's super easy. You begin a transaction. You find the existing orders. You find the credit limit. Do some calculation. If there's sufficient credit, create a new order, commit the transaction. And if you're running at a sufficient isolation level, this ACID transaction will guarantee that if there were simultaneous attempts to access, to create orders for the same customer, that business rule is enforced. But in this model, orders belong to one service, customers are in another service. You can't write a database transaction that looked like this. And then if you did, you'd have to have some form of distributed transaction. And, you know, two-phase commit, XA, that kind of technology. And basically, as was mentioned in Randy's talk, people just don't do this kind of thing anymore, right? It is simply not fashionable or not practical in order to do this. And all of our cool modern tech, I mean, there's a bunch of like technical issues why two-phase commit is problematic. you know, the cool new technology generally does not support it, right? And then you've got the CAP theorem that says you basically have to choose between a consistency and availability, and people prefer to be available, so there goes consistency. So that's sort of a problem. So we kind of have to we're in a microservice architecture, we're giving up on our regular ACID model. And someone at eBay coined the term BASE, basically available, soft state, eventually consistent, which sort of describes this new transaction model. Interesting, later on, I'm going to actually describe how Sagas are actually ACD. They just don't give you the I, but so that's kind of another acronym, but BASE sounds cool. So we can't use two-phase commit to enforce this credit limit. So what do? So that's where this concept of a saga is really useful. And that comes from a 1987 paper. So yes, they had computers back then. Just didn't start with the web and all. Anyway, so it's sort of an adaptation of this saga principle. And there the idea was, instead of having long transactions that hold on to locks, you break them up into a sequence of short transactions, and each one commits at each stage. So that's the general idea. So it sort of looks like this. So instead of having one big transaction that spans all of the services, you have a series of local transactions, one in each service, and they're actually strung together using some form of messaging or events. So one service does something, publishes a message that triggers something in another service, and so it goes on until the saga completes. So in the case of creating an order, it looks something like this. Request comes in to create an order. It will create, the order service creates an order in this pending state. So someone can actually look up the status of the order. So it's kind of created, it just hasn't been verified. And then another transaction occurs in the customer service to attempt to reserve credit. And then, assuming that is successful, another transaction will occur in the order service to approve the order. So we've got a series of 3 local transactions in order to create an order and verify it, or reserve credit. So on the surface, this sort of sounds fairly straightforward, and and in some ways it is. But there are some tricky issues that you have to deal with. So one is, imagine you could be 5 steps into a saga and you've decided that you cannot proceed because a business rule will be violated. Well, you have to undo the preceding 4 steps. In an ACID transaction, that would be trivial. You just execute a rollback statement, and it's as if those updates had never happened. In a saga, you have to explicitly code this. You've got to write what are known as compensating transactions to undo what you did before. So conceptually, then, a saga looks like this. It's a sequence of forward transactions, T1, T2, T3, and so on. Each one of those T transactions has a corresponding C transaction, C1, C2, and so on, that undoes what it did. So in this model, imagine we execute T1, that's committed, then we attempt to execute T2, that fails. We then have to execute C1 to undo what T1 did. So it would go T1, T2, and C1. And that all has to be kind of coordinated and sequenced and made reliable, because we want to ensure that either all of the T's execute or all of the T's that were executed had their corresponding C transaction executed to undo what was done. So it's kind of tricky. In the case of creating orders, the compensating transaction is actually to reject the order if you can't reserve credit. So that's one complication, but it's sort of a matter of programming to just get that right, and it's not too difficult. What's a little more interesting is now what was previously sort of a synchronous transaction has now become an asynchronous operation. So we've got our synchronous REST API triggering an asynchronous Saga. And so the issue is like, well, hey, when do we send back a request? So I send back a response to the request. And there's sort of two options. One, you could actually, the service could actually wait until the Saga completes. That's good because the response would specify the outcome of that Saga. The order was approved, the order was rejected. It would be bad because you're sort of waiting on all of those services to sort of respond, and it kind of impacts the availability of that particular API. So it's actually nicer to sort of introduce some asynchronicity into the API so the service can send back a response immediately saying, well, I've received your request to create an order and I'm thinking about it. That downside is the client has to then poll to see whether that order has been placed. So that's nice, though, because it does improve availability. No one really has to kind of be up for the entire time because the message broker will guarantee that messages will eventually be processed. So the API then changes, right, where create order just says, well, here's the order ID, and check back later by calling get order if you want to know whether the order has been approved or rejected. This doesn't necessarily impact the outcome doesn't impact the user experience, though, because the UI, like, you have a bunch of JavaScript running in the browser, it can actually hide this asynchronicity from the user. It's like when you place a credit card and a dialog box pops up saying, don't hit the back button, right? You can do it slicker than that, but in general, the JavaScript in your UI can actually hide the polling and so on, and the server could even push the notification of approval or rejection down to the UI, so you get a pretty responsive UI. So the API is different. The user experience does not have to change. But then there's this really tricky issue, which is you don't actually have any isolation. So you go back to ACID, right? The I is isolation. Well, there's not any. You don't have that anymore because each step of a Saga is a local transaction that commits its changes. So we've got these two, from the perspective of the sort of the order service, we've got these two transactions, right? And then another request could come in to cancel that order. And that's kind of interesting. Now we've got this situation which we never had before, where the user's requesting that we cancel this order in a pending state. And that's kind of a little strange because this create order Saga is still in the middle of sort of processing it. So how do we handle that, right? So one is you could just say, the order's pending, you can't cancel it right now. So that would be sort of a poor user experience. Maybe you could interrupt the order Saga, somehow create order Saga, somehow set a flag saying, well, you were in the middle of validating it, but the users requested that it be canceled, so you could set a flag, and that could trigger that could cause the create order Saga to roll back. That's not bad. But then it does mean that, well, perhaps the create order Saga needs to know a bit more about the cancel order Saga than you'd otherwise want it to. And then another option, which is kind of interesting, is that the cancel order Saga could wait for the create order Saga to be completed. Though that suspiciously sounds like distributed locking. But maybe that's okay, because that's sort of kind of like if you've got this domain object that's in the middle of being worked on by a Saga, it's kind of nice to wait for that other Saga to complete before trying to perform another operation on it. It's kind of like reminiscent of the actor model where you've got a mailbox where if the actor's in a particular state, the messages get stashed until the actor returns to a state where it can process them. There's some kind of analogies there. So there's some interesting design issues that can arise, in this create cancel order scenario from the lack of isolation. And I was sort of troubled by this, and I was like looking around in the literature to find some sort of, I don't know, academic paper to tell me what was going wrong here, right? And then I found this paper back from 1998, so not quite that old. It was about, they have what they call a countermeasure transaction model, which I thought was a fantastic term. And the idea is they have about a bunch of countermeasures to kind of deal with the isolation anomalies that are resulting from the lack of isolation. And they have an interesting way of describing sort of these long-term transactions or sagas. So their model is, one of these sagas is a series of compensatable transactions, so things that can be undone. Then they have this interesting notion of a pivot transaction, which is something that can't be undone. Like it either has to work or be rolled back, or if it commits, then that's like you're fully committed to this transaction, which is kind of an interesting concept that I'm not sure applies in the model I'm presenting here. But then once you've committed, you've got this series of what they call retriable transactions that are just things that you can do sort of asynchronously after the pivot transaction is committed. And that could be like arranging to send out emails. Just kind of interesting. It's sort of an interesting way of making a distinction between things that can fail and need to be undone versus things that can just be done and will never fail for business reasons. So it was kind of thought-provoking. So in their mind, sagas are actually ACD. So they're atomic in the sense that all of the forward transactions will be executed or they will all be compensated. So I thought that was, which is a little different perhaps from some of the definitions of atomicity. So it doesn't appear as one thing, but there is this guarantee that all of it will happen or all of it or none of it will happen effectively because of the compensating transactions. It's also consistent because you have referential integrity within a service because of referential integrity constraints in that database. But if you want, but then referential integrity across services is handled by the application. And that came up in Randy's talk. And it's also durable as well because things do get committed locally. They get put in a message broker that guarantees that it's durable as well. But what's missing is this I. And that can cause a set of anomalies. And so these are sort of from classic kind of database literature, right, where you can have lost updates where, one step of a saga can read an object, some other transaction can go in and modify it, and then a later step of that transaction or a compensating step can overwrite that intermediate update. And then you can have dirty reads as well, where a saga writes, some other transaction reads, and then that compensating transaction is executed to like undo what was done. So the intermediate transaction read a value that was only there temporarily. And then a saga can exhibit sort of these non-repeatable or fuzzy reads where one step of it reads a value, some other transaction writes that value, then later on the saga rereads that value, gets a different value back. So this is all from lack of isolation. So to solve this, they described a set of countermeasures for solving these problems. And I'm just going to summarize them here. So one thing to do is just to try and make the updates commutative. So sort of, if you think about basic arithmetic, adds and subtracts are commutative, for instance, right? You can do them in any order and the outcome is the same. So that's one way to deal with these isolation anomalies. There's another approach which they call a version file, which is kind of strange terminology. But the idea there is that you record a history of changes, and then you can use those to sort of reorder the updates to make them commutative. And what was interesting, is it Katie from, is it Twitter, gave a talk about Sagas somewhere else. And she in her talk, she gave an example where creating a reservation and canceling a reservation needed to be commutative, which meant that you could, because those requests could arrive out of order, which was really, really interesting in this notion that you could cancel a reservation before you made it. But that to me sounded like an example of a version file. So when the cancel arrives and there's no corresponding reservation, you record the fact that you received the cancel so that when the create comes along, you just know to not execute it, which is kind of interesting. This also sounds a bit like event sourcing, where you're recording the history of changes. And then they talked about another countermeasure was rereading values. So TI reads it, well, a later one can then reread it just to make sure the value hasn't changed. And if it has, perhaps abort that Saga and retry it from the beginning. So you can sort of roll back and then restart. And then another one was this pessimistic view, which was sort of an interesting thing because it stressed minimizing business risk. So the idea is if you're going to increase someone's credit, do it once you know that that transaction won't be compensated, right? So there's this notion that you can reduce credit and then increase it later because that's not going to introduce a business risk. I guess it would cause a lost sale, which is another, but that's sort of maybe less risky than reducing the credit, processing a sale, and then in a compensating transaction, reducing the available credit, which means that that sale should never have happened. So that's kind of an interesting idea, is that your data is inconsistent and your application is not working in a perfect way according to ACID transactions, but you make it behave in this imperfect way that minimizes the risk to the business. And I thought that was interesting. And then they also had some strategies, which were, one was countermeasure by value. They actually said, well, if there's this really high-risk transaction, someone's trying to transfer or place a huge order, then use a distributed transaction at that point because it's too risky to do anything else. And I thought that was interesting. And then the other thing they had, the final one, was basically semantic locking, so locking at the application level, which is kind of like the cancel order scenario saga waiting for the create order saga to complete, which I thought was, that struck me as an interesting approach. I mean, it's basically an application level distributed lock. So you need to implement some kind of deadlock detection in order to time out if there's some failure or something like that. The other approach they suggested along these lines is to set a flag to say, this bank account is in the middle of being updated. So when you're doing some form of reporting, treat it differently. Like if an account is not in the middle of being updated by a Saga, then you know that the balance is accurate. Whereas if it's in the middle of being updated by a Saga, well, put that in the fuzzy balance column because we don't really know what the value is just yet. So I thought it was kind of interesting. So so there's a whole bunch of tricky issues that you have to deal with, but it's sort of like you go search the literature, and people have been thinking of ways to reduce the risk at the application level. So quite intriguing. So that's kind of Sagas, and now kind of want to get back to sort of less scary things, the actual technical sort of implementation of the sagas, starting with how to coordinate and sequence the series of steps. Okay, so conceptually, right, saga is a sequence of steps. They have to happen one after the other. Maybe there's branching, but I'm ignoring that. And then if there's a failure, you then have to execute the compensating transactions in reverse order. So there needs to be some logic somewhere to make this decision. And if this sounds sort of like kind of workflow, I think there's some strong similarities. And so the solutions are kind of the same, where there's two approaches: choreography, where the decision making is sort of implicit and distributed amongst the participants. And then there's orchestration, where you actually, as you're going to see, you have basically a domain object telling the participants what to do. So with choreography, I always get them mixed up in my head. Basically, you can do that in a very trivial way using events. So, for instance, with the order service, when a request comes in to create an order, it can create an order and publish an event. That event gets consumed by the customer service, which will then attempt to reserve credit for that order. And then it will publish an event saying, yes, the credit was reserved or the credit limit was exceeded. The order service would then receive that event and either approve or reject that order. So you just got these services that just emit events, receive events, perform some action, emit more events. And eventually this saga completes. And interestingly, I think it was at QCon 3 years ago, I gave a talk about event sourcing, and I might have used this slide, but I didn't have a word for it. So it's like kind of subsequently I discovered what I was talking about was something that could be labeled choreography-based coordination using events. But it was just sort of like very natural, because event sourcing is basically where you're using events to persist the state of your domain objects. So whenever a domain object changes, you just publish an event, just kind of like I described here. So it's really trivial to sort of implement these choreography-based sagas in an event sourcing application. It's sort of this natural way. And also, in this model, the sagas are all loosely coupled. They're just kind of exchanging events, and it all kind of works. But there are some interesting issues in the sense that, there's a cyclic dependency because the customer service is listening to events from the order service and vice versa. And, from a design point of view, should you really have cycles? Maybe not. Maybe that's not such a good idea. And also the domain objects potentially have to know a lot about what's going on. So in the case of the order, some logic in the order service has to know, oh yeah, when the event comes in from the customer service, I have to kind of approve the order. But then it might get a lot more complicated if there are other validations that need to be done, such as reserving inventory and so on. So there's sort of all this event processing logic mixed up with the business logic. And then also events are a very indirect sort of way of causing things to happen. I mean, I remember, because an event is something that has happened, like an order was created, an order was approved, credit was reserved, or credit limit exceeded. And sometimes you just want to tell a participant what to do, just direct it rather than sort of indirectly suggesting, hinting strongly via an event that it should maybe consider doing something. So that kind of then leads you to another model where you have where you implement sagas using orchestration. And that's where you have an object that's basically like this little workflow that's directing the participants, telling them what to do. So in this model, as you're going to see, when the order gets created, as part of that, you get this create order Saga object, which it then just goes and tells the customer service what to do, the order service what to do. So it's a lot more direct, none of this indirection sort of hinting via event. So in this model, you have a Saga orchestrator, which I actually shortened to the term Saga. And that's actually a persistent object, so it lives in the database that tracks the state of the Saga, the workflow, and then tells the participants what to do. So it will tell one participant to execute a T1, another and when that has succeeded, it tells another participant to execute a T2, and so on. And then if there's a failure, it will start executing the compensating transactions one by one. And as you're going to see later on, actually send command messages to the participants. So there's this sort of, it's all done via a message broker, but instead of events, it's commands saying do this, and then eventually a reply will come back. So kind of the behavior of this Saga or Saga orchestrator is when it's created, it tells the Saga participant what to do. Then a reply comes back, at which point it figures out which is the next Saga participant to invoke next. And based on whether that transaction was successful or not. And then it tells the Saga participant, sends it a message, and then it updates its state, which is persisted in the database, and it just kind of goes around that loop until it runs out of things to do, at which point, presumably, it is done. So in this model, it works like this, where the request comes in to create an order. It actually creates an order, and it creates a create order Saga, which maybe should be called validate order creation Saga or something, except that I know it's debatable what the term is. And that then tells the customer service to reserve credit. So it's asynchronously invoking an operation on the customer service, which is then going to send a message back saying, oh, the credit's been reserved. So it's sending back a reply message indicating the outcome of that credit reservation. And then the create order Saga, when it gets it, will, in this case, approve the order. If it was credit limit exceeded reply, it would reject the order. So that's kind of the idea. So in terms of the code, this is actually what it looks like. I'm just going to talk about this quickly. You can go see it online. So there's a simple Saga interface, and it's a generic type. And what we're looking at here is like a stateless singleton. And then create order Saga data is the actual state of any particular Saga object. The workflow is defined by this sort of simple DSL. There's a series of steps. Each step invokes either a participant or it executes a compensating transaction. And all it's doing is invoking these methods that create a command message to send to a particular participant. So in this example, it's sending a reserve credit command to the customer service. So a bunch of details there, but the logic is fairly straightforward. And then inside the customer service, there's a bunch of command handlers. So this is just a layer of abstraction over a message broker, and actually Kafka to be more precise, where messages have a header and a body, and there's particular semantics to each one. So in this example, when it gets a reserve credit command, it invokes the reserve credit command handler, which basically just implements the usual domain logic, finds the customer object in the database, executes the reserve credit method on it, and then sends back, returns a success reply. Otherwise, if it throws an exception, it returns a failure reply. So that's all. So it's just this layer of abstraction over message sending. So in the framework, you can, for doing this, you can, if you go look in GitHub, eventuate, kind of came up with this name TRAM, transactional messaging, because this is all tied in with, so the sending and receiving of messaging is tied in with database transactions. But it's not using JTA and JMS, it's using a different approach. So anyway, so that's what a Saga looks like. I mean, the nice thing about these Saga orchestrators is the logic is centralized in one place. You know, the customer in this case doesn't know a whole lot. It's not listening to all of the order lifecycle events and knowing whether to reserve credit or release credit. It's just being told what to do. So that reduces coupling, and it actually reduces cyclic dependencies as well. One downside is there's always a risk of having kind of these smart Saga objects telling the dumb participants what to do. But I think that's just a matter of careful design. So that's the orchestration part. So that's sort of the high level. How do you sequence this series of local transactions, and how do you deal with compensation and so on? So yeah, simple framework that just makes defining that quite straightforward. And it's sort of similar to what you might get with some kind of traditional sort of workflow engine. I mean, the main difference is it's very focused on implementing sort of Sagas as opposed to more general purpose workflows. And then the other difference is, as I'm going to talk about now, it's actually based on sort of transactional messaging, because there seems to be this whole big gap where I want to reliably send a message and update the database atomically, and frameworks don't seem to do that very well. The assumption is you use two-phase commit, which you can't in this situation. So anyway, so if we look at how messaging needs to work, right? So the Saga orchestrator needs to send a command to a participant telling it what to do. And then the Saga participant has to send back a reply. And this all has to happen even if there are transient failures. So, you know, maybe the Saga participant is down. Maybe the Saga orchestrator sends the message and then goes down, but you want it to respond to the reply. And for me, that actually means that you really want to do this on top of a messaging broker, as opposed to some form of retriable RPC. Interestingly, during the panel, Lewis from Google said that Google doesn't really use message brokers. They do retriable RPC for a bunch of reasons. Not entirely I don't know how to adapt that to this model. To me, it's like you get a lot of simplicity by just relying on your message broker to do the right thing. And it doesn't require the participants to sort of be up and available. So the model ends up looking like this, where the create order Saga sends a command to a participant's request channel. Think Kafka topic. So the customer service has a customer request channel, which it's reading from, processing those messages, and then it's going to write the reply to the message channel that's specified in the reply to header of the message, reserve credit. So the Saga reply channel, which then gets read by the Saga, and so the process goes on. So that's the easy part. There's just some sort of simple messaging. The tricky part is making this happen transactionally, because at each step, the Saga is updating its state and wants to send a message. Likewise, the participant is updating its state and wants to send a reply. And all of this has to happen basically atomically. But the trick is that we can't use the classic approach of sort of, two-phase commit. A JTA transaction spanning, our JDBC database and our JMS message queue, right? Because that's, especially JMS, that's sort of old school technology, and we don't want to use JTA. So it's sort of like, how do we do these two things atomically? And that's sort of kind of the underlying foundation for this Saga framework. And the way it works kind of took inspiration from how eBay did this. And basically the model is this. So you have a message table. So that basically acts as an outbox for a service. So in this case, when the customer service updates its database and it wants to send an order created message, that doesn't make sense. Typo on the slide. So the idea is, so when a service wants to update its database, which obviously has to be done inside a transaction, as part of that transaction, it will insert a message into a message table. And that's a local ACID transaction, so it's guaranteed to be atomic. So that's step number one. So that's kind of it from the perspective of that service. And then there's a separate process that is pulling messages out of that table and publishing them to a message broker. So we've sort of broken it down into two steps. The first step gives us the atomicity that we need, and we're just going to assume that this message publisher is going to keep trying until it's actually published the message. And there's actually two ways it could do this. One way, which is generic and works with a whole bunch of different databases, is basically to poll the message table. Select from messages where the message is new and hasn't been published. So that can work. That's sort of a generic approach. A much better approach is actually to tail the transaction log. So actually look in the MySQL bin log, see the series of inserts into the message table, publish them to Kafka, or look at, each database has its own particular transaction log. Mongo even has an op log, so you could look in that to see the changes and then know to publish them to a message broker. And that's a much sort of kind of lower latency, pure, nicer way to do this. So the framework that I work on is called Tram, that actually implements that. So that's like a whole bunch of messaging abstractions that are based on the mechanism that I described on the past couple of slides. So then the other option is actually to use event sourcing, kind of as sort of a reliable foundation. Because when you basically, say when an order or a customer is created, well, that's going to result in an event being saved or published in an event store. And that can actually reliably be turned into a command or message that's sent to some other service. So there's a couple of different mechanisms for implementing this. It's an absolutely fascinating area. But the key point is that in order for this to work reliably, you need some form of transactional messaging, and transactional in the database sense of the word. Anyway, so that's my talk. Hope that you found it useful. So in summary, right, like the whole point of using microservices is to tackle complexity, or as someone pointed out, slow the growth curve of complexity. And accelerate development, right? Database services, a database per service is essential for loose coupling, right? It's enabling the teams to work autonomously. And the way you want to maintain data consistency between services is using Sagas. And then the underlying sort of platform that the Sagas are built on is this transactional mechanism that enables you to atomically update the database and publish a message. So that's my talk. Thank you for listening, and I hope that you found it useful.